Hey guys, this is Nick from EEGuru.com. Today we're going to be talking about electrical resistance. So what is electrical resistance? Let's say we've got our bucket again. This time our bucket of water is just going to be hanging on a little hook, right? There's a little hook right here, and the bucket's still filled with water. Okay, so let's say this time that we've got a pipe coming out the bottom of this bucket. It's a relatively narrow pipe. Let's just think of it as a little bit more narrow. And we poke a hole in the bottom of this bucket. And the water is going to rush out, right? So let's compare this bucket to another bucket. So what if we took the same bucket and we closed off just a little bit of this here? We made the pipe a little bit smaller. How is that going to affect the flow? Is there going to be more or less resistance to water over here? Well, there's going to be more resistance. If the little opening is smaller, it's going to be more difficult for the water to flow through this little channel. So in this case, resistance increases. Okay, so let's look at this from an electrical standpoint. And that electron's flowing that way. Okay, so first of all, our resistance is proportional to something called resistivity. And we mark resistivity by this little rho right here. It's the Greek letter rho. Now, resistivity is something that's a constant in the material. So copper has a really low resistivity, while something like the wood that your desk is made of has a really high resistivity. So it's really a measure of how well your material can conduct electricity, or how poorly it can conduct electricity, because it's going to be higher for wood than it is for copper, or something like that. So if you have, let's say, steel is going to be a relatively good conductor. It's going to conduct electricity very well. So it's going to have a high or a very low resistivity, because it's not very resistive as a material to electron flow. So that's the first part of this equation. Now, we're going to define this guy right here. Oh, let's bring up the pen. As the area of the cylinder, and then this over here as the length of the cylinder or the wire. So let's see if we can think about what happens if we increase the area of this cylinder. What if we made the cylinder twice as big as it was before? Let's go back up here. We made this pipe smaller and the resistance went up. So what do you think is going to happen to the electrons if we do the same thing? If we make this opening here bigger, what's going to happen to the resistance? The resistance is going to go down. There's more room over here for the water to flow. So if we make this opening bigger, there's going to be more room for the electrons to flow. Okay, so the way we're going to write that is we're going to put area on the bottom of this equation. Okay, so let's think about the length. If we make our length longer, is it going to make this section of wire more or less resistive? Is it going to be easier for this electron to flow through twice as much of that material, or is it going to be easier for it to flow through twice as much of that material? So the way that we can think about that is, what if we took this and we made this pipe over here, and we made it even more of this small gap that it has to go through? Is that going to make the resistance go up or down? Well, it's going to make it go up, right? It's going to be harder if this little gap is longer than if it's over here and there's nothing there at all. So we're going to put L on top of this equation. And that's your whole equation, guys, right there. Well, I guess this should be an equal sign now, shouldn't it? So let's just rewrite it. And that's your takeaway. That's how you calculate that, guys.